Today we are going to be looking at the physics behind this golf shot by David Sloan III. We are going to analyze the physics behind this amazing shot. So let's watch the clip. We are going to be looking at the physics behind the inclined plane at the end of the shot, the projectile motion of the ball through the air, the impulse momentum of the club hitting the ball, and the circular motion of the club itself. First, to analyze the physics behind the inclined plane is Keegan Fish. Go.
So now we're going to be observing the inclined plane that the golf ball travels along, and about the speed at which it goes down that inclined plane. For this, we're going to assume the inclined plane is approximately 10 degrees, pretty slight, not bigger than what we probably expect on most golf course greens. So we draw the free body diagram. Of course, the ball we've got the force of gravity acting down on the ball, and then the normal force here. The mass of the golf ball is approximately 0.04593 kilograms, and the force of gravity is 9.8 meters per second squared. So from there we go over to force equals mass times acceleration. Of course, we know that the mass is 0.04593, and then we multiply that by the force of gravity, 9.8. So for F, for the force of gravity upon the ball, we get 0.450114 newtons. We'll take that down to here to find the x component for which the ball is traveling on. So F of x would equal F sine theta. We're going to take the F we got here and bring it down here. So we get F of x equals 0.450114 times sine of 10, 10 being the angle of the center. Therefore, we can get the F of x would equal 0.07816 newtons. From there, we go to force equals mass times acceleration again. As shown by the arrow, we'll just take this and bring it up to here. So it would be 0.07816 times mass times equals mass times acceleration, 0.04593 times the acceleration we're getting determined. From there, once we determine it, we get that A is approximately 1.7 meters per second squared. And now we're going to observe the projectile motion of the ball with Brian.
So now we are going to be analyzing the actual flight of the ball during this amazing shot. We're going to be looking at the projectile motion. Specifically, we're going to try and find the initial velocity that the ball took off at. So we can look at this equation, x equals VOT plus XO. This specifically refers to the speed of the ball in the x direction. In other words, along this way. Because we know that the only acceleration acting on the ball while it's in midair is actually due to gravity, which is in the y direction. So we can ignore that for now if we're looking at the initial velocity of this ball. So, and furthermore, we can take the XO out because we can just assume that XO was 0. So now we have x equals VOT, the initial velocity times time. Fortunately, we know the distance that the ball traveled, approximately 90.13 meters, and we can measure from the video the time it took for it to travel that distance, about 6.36 seconds. From that, we can determine, just simply by dividing, that the initial velocity in the x direction was 14.17 meters per second. But this is only in the x direction. If we look here, we can split up the initial velocity into two components, x and y. Now, in order to actually take into account the initial velocity, we need to recombine these two components because we have the x, and now we need to find this line here. So simply we know that cosine 12.85, because 12.85 is the approximate angle. Thank you to the PGA for keeping amazing statistics. Cosine 12.85 equals 14.17 over x. In other words, cosine equals adjacent over hypotenuse. And simply by multiplying by x and then dividing by cosine 12.85, we can determine that x, the initial velocity of this ball, is 14.53 meters per second. So during this entire flight, the ball is launched at 14.53 meters per second and moves approximately 90.13 meters. Now we're going to take a look at the impulse momentum for when the club hits the ball. Thank you. Go.
So now we're going to be looking at the impulse momentum as the club hits the ball. We can do that by looking at the equation P equals mv. So we have the 0.04595, which as we explained earlier was the mass of the ball, times 14.53, which is the velocity that Brian found when he was talking about the projectile motion. So with that knowledge, we have P equals 0.667 Newton seconds. So then we do F times T equals delta P. So F times 0.01, which is about what we estimated to be the amount of time between the ball and the club. You set that equal to 0.667. And then from there we got F equals 667.59 newtons. And of course, keep in mind that in reality, some of this energy would be lost in sound. Back to Brian.
So far we've looked at the speed and force on the ball, but now we're going to look at the speed and force on the player using circular motion. So we know that the circular acceleration equals v squared over r, and we know that F equals ma, force equals mass times acceleration. So if we want to look at the centripetal force, we simply take the mass times this v squared over r, and we end up with the equation SC equals mv squared over r. And this will tell us the centripetal force, how much force is on the player's arm as he swings the club. So we plug in numbers, 0.68, the approximate weight of the club, times 51.46, the approximate speed, thanks to PGA, and square that, and then we take that over the radius, which was his arm plus the club, and we end up with a total centripetal force of 1,028.99 newtons. Again, that's how much force is on his arms pulling up on the club to make that circular motion. Now, we can also look at tangential force. In other words, the force pushing the club in a tangent to that circular motion. So to look at tangential force, we need to look at tangential acceleration. To do that, we took this arc divided by the amount of time it took to get up to that speed. Sorry, this is the speed. And the amount of time it took to get up to that speed. And so that gave us the acceleration of 88.72 meters per second squared. Now, since Ft equals mass times acceleration, we can find the tangential force. We simply multiply our 88.72 times the mass of the club, 0.68, and we end up with 60.33 newtons. That's the tangential force. And from there, we can actually look at torque, the pressure on it in that motion. So we take this tangential force and we multiply it by the length of his arm up to his shoulder to look at the torque on him. And that gives us 36.80 Newton meters. So we can see here the centripetal force, the tangential force, and the torque on the player as he makes this amazing shot.